Hey AP, in this video we are going to talk about looking at weak acids and weak bases. So with a weak acid and a weak base, we have already talked about what makes something weak. It's that they don't fully dissociate. So if they don't fully dissociate, that is like saying that they don't fully dissolve in water. And we've looked at things that don't fully dissolve in water when in our last unit we looked at salts that don't fully dissolve in water. And for those, we had special K values, equilibrium values called KSPs. And we said that, well, if they don't fully dissociate, the change in the concentration of the original salt, and in this case, we're going to look at acids, they don't matter. And so we're going to follow that same practice here, except now we're looking at Ka values for acids and Kb values for bases, which are specific equilibrium constants for acids that have the A, and for bases that have the B. So for weak acids, we say that they have a Ka value. Their Ka value is their equilibrium constant. Remember that weak acids, because they're weak, means they don't fully dissociate. And then a relationship with the Ka value and pKa value, just like with pH and H+, if I have a low pH value, that means I have my hydrogen ion concentration is pretty big, right? It means I have a lot of hydrogen ions present in solution. If I have a low pH, it's super acidic. And then vice versa, if I have a really small hydrogen ion concentration, that means it's not very acidic, so I'm going to have a higher pH. Well, that same relationship applies to our Ka value, and then we can take the potential of our equilibrium constant and have a pKa value, just like we can take the potential of our hydrogen ion concentration and have a pH. So we see both of these. So the smaller the Ka, the less it dissociates. And the less it dissociates, that means the weaker it is. So we're going to have a larger pKa value. Okay, so again, same relationship as pH in H+. So let's take a look at this. One thing to note, if yours says aqueous right here after water, water is not aqueous, it's a liquid. So may I go ahead and make that change. If I were to look at how a generic acid, so acids start with hydrogen and then it's their anion, generic acid dissolves in water. Again, it's at equilibrium because I'm looking at weak acids. Okay, if this was a strong acid, this would be a single arrow. But I'm looking at weak acids. Dissociates into hydrogen or hydronium ions here because the acid is going to give its hydrogen to the water. Water is going to accept it, and then the anion loses it. So if I'm starting with some amount, we'll say Y, some concentration of my acid. Remember, we don't care about liquids. And originally, before it dissolves, I have neither of my hydronium ions or anions in solution. It's going to change by some amount, X, based off of the stoichiometric coefficients, right? Balanced coefficients in my reaction. And then I put it together. So Y minus X, X, and X. Now, just like before, we were talking about weak acids, or we're talking about insoluble salts. We said that the amount of change compared to my original concentration doesn't matter. Same thing here. So again, this is insignificant. So we don't have to worry about it. So we can ignore the X here, which is great because that makes our lives easier when it comes to the math in terms of solving for our Ka value or our concentration that we're trying to find here. So if I were to write my Ka value, same thing as before, products over reactants raised to their coefficients. So my two products, again, these are concentrations, so I have to have brackets. A minus my two products over my original acid. And again, I don't include water because it is a liquid. And then if I want the pKa, just like going from hydrogen ion to pH, I take the negative log of that. Same thing here. pKa is the negative log of my Ka value. Okay. And you'll see this formula is on our formula sheet underneath equilibrium. So we are looking here at Ka, right? Hydrogen ions and anions. So you can write it as H plus or you can write it as H3O plus. Either one means the same thing. We're going to have our Kb, and then we're also going to have our Ka and Kb. We see them here. We can figure them out based on Kw, and that is our constant for water. And then we can also see down here, we have our pKa is the negative log of our Ka, pKb, negative log of Kb, and we'll get to this formula in a couple of videos. So we're dealing with this section still in equilibrium. Now we're just looking at specifically equilibrium in terms of acids and bases. And then we've got our equilibrium constant. This is a reminder of, hey, this is what everything is. Kp is gas pressures, Kc is molar concentrations, weak acid, weak base, and water. Let's do an example. So what's the pH of a 1 molar solution of ethanoic acid? Well, the nice thing about weak acid equilibrium concentrations and calculations is it doesn't really matter what the acid is, as long as it's a monoprotic, meaning it just has one hydrogen ion, and it would tell you otherwise. So I'm just going to write ethanoic acid. And that is going to, I'm going to look at how it dissociates or dissolves in water. It's a weak acid, so I'm going to get H3O plus, and I'm going to get A minus, because it's going to drop its hydrogen. I'm going to make my ice chart. Water is a liquid, so it doesn't matter. And we would be given in here our Ka value for ethanoic acid. You look it up in a table, 1.82 times 10 to the negative 5. In the front of your packet, there should also be a table of Ka values. And if not, you can always look up tables of Ka values. You never be asked to memorize them. They'd be given to you. So we're told initially we have a concentration of 1.0 molar ethanoic acid, nothing for our hydronium or our anion. Change of minus x, plus x, plus x, 1 minus x, x, and x. And again, this is a weak acid, so this part, my change over here, is insignificant, so I can ignore it. My Ka equation is our H3O plus times our A minus over our HA. So I go ahead and plug in 1.82 times 10 to the negative 5. These are both x. I get x squared over 1. Solving for x, right? X squared, so I take the square root of both sides. I get 0.00427. And I am asked to find pH. And from pH, I can get pH from my hydrogen ion concentration, which is the same as my hydronium ion concentration. So that means that my hydronium ion concentration, which is just the longer way of writing my hydrogen ion concentration, is 0.00427 molar. And we learned in our last video that pH is equal to the negative log of my hydrogen ion concentration. So pH of the negative log of my hydrogen ion concentration, I'm going to plug that in by using our log button here. So negative log 0.00427, and I get 2.37. So my pH 2.37, which makes sense. This is an acid, it's acidic, and it has an acidic pH. What if I want to go the other direction? What if I want to calculate the Ka based off of a concentration of a weak acid with its known hydrogen ion concentration? Well, again, for a generic acid in water, I have H3O plus and A minus. Okay. This is clearly at equilibrium. I'm asked to find Ka. So at my equilibrium, I have a 0.1 molar HA. Water doesn't matter. And this is a monoprotic acid. There's just one hydrogen on the front. Haven't been told otherwise. So these have a 1-to-1 ratio. So that means that if I have 1.75 times 10 to the negative 3 molar hydronium ion concentration or hydrogen ion concentration, that's also the same as my concentration of my anion in solution because it's a 1-to-1 ratio. The change in X, right, is the same for both of them. So I'm looking for Ka, H3O plus, A minus over HA. I plug in 1.75 times 10 to the negative 3. That's squared over my 0.1 molar that I had to start. I'll write this underneath because I'm running out of room. And when I plug that in my calculator, I get 3.06 times 10 to the negative 5. And just like our other Ka values, no units on them. Let's look at weak bases. Well, weak bases are going to work the same way as weak acids. So for a weak base, we have our equilibrium constant. Let's just say weak bases, which is Kb. Again, weak bases don't fully dissociate. That's what makes them weak by definition. And the smaller the Kb, the less it dissociates, the weaker the base. Therefore, the larger the pKb. So again, same relationship in here that we had in our pH and our hydrogen ion concentration, or our pOH in our hydroxide ion concentration. So our generic formula for a base that is dissociating, we could either use something like ammonia, NH3, or we could say just B for base. And I'm actually going to write above this. This would be BH plus, and then OH. We'll use these. They're more generic, which will be more helpful for us later on. So some base in water, again, this should be liquid water, and our base in liquid water, water is going to donate its hydrogen to the base, so it's going to become BH plus, and then water loses its acidic hydrogen, so it becomes OH. So again, if I have some amount Y, I don't care about my liquid, and I have no concentration of my acidic base now, or OH, minus X plus X plus X, Y minus X, X, and X. So just like before, because this is a weak base, this change in X for its original concentration is insignificant. So we don't have to worry about it again, which is awesome. So my Kb, just like before, products of reactants raise their coefficients. So products, BH plus, other product, OH minus, both 1 to 1, so nothing else added there, times or over my concentration of my base. Again, I don't include water. And then just like before, my relationship between Kb and pKb is the negative log of my Kb is equal to my pKb. So again, these formulas are also on your reference guide underneath equilibrium. So let's go through a couple of examples, just like before. So example 3, what is the pH of a 0.44 molar solution of ammonia? Well, ammonia is a weak base. It's a weak base, and it's NH3. We've seen it a few times. We've just never classified it as necessarily being a weak base, but that's what it is. So NH3 is in water. It's weak, so I draw my double arrow. It's a base, so it's going to accept a hydrogen, so it becomes NH4 plus. And then water is OH minus. At equilibrium, so I make my ice chart. I'm told that I'm starting with a 0.4 molar solution. 0.44 molar. Water is a liquid, so I don't care. 0 and 0. They are all 1 to 1 to 1. So X, X, X. And this is insignificant, so that stays as 0.44, X and X. So we would be given our Kb value, because it's not given to us. We could look it up in a chart. And when we do that, we find that our Kb value is 1.78 times 10 to the negative 5 for ammonia. Oh, one thing to note that I didn't say something about on the previous page, if you look up the K, like a Kb value or a Ka value, and you're only given one, most of the time you're just given a chart of Ka values. To figure out the Kb value, Ka times Kb equals Kw, and Kw is our equilibrium constant for water, which is 1 times 10 to the negative 14. And this is the same as our hydrogen ion concentration times our hydroxide ion concentration is 1 times 10 to the negative 14. So it's the same thing, same formula. And that formula is also on your sheet. Yep. it's on your sheet as well. So just make a note of that, depending upon what you're given when you look something up. All right, so again, Kb for here is our NH4 plus and our OH minus, both to the 1, NH3. Now I plug everything in, 1.78 times 10 to the negative 5, x and x, so I get x squared on top, and then 0.44 on the bottom. Solving for x, I get x to be 0.002799, and that is the same as my hydroxide concentration and my conjugate acid, NH4 plus. I'm asked to find pH, and I'm given OH because it's a weak base. So if I know that my concentration of hydroxide ions is 0.002779, I can figure out my pOH because that's the negative log of my OH concentration. So when I plug that in, I get 2.55, right? I plug in negative log this number, I get 2.55. And then remember that pH is equal to 14 minus my pOH. So plugging that in for here, I get that equal to 11.4. So the pH of my solution, 11.4, that is a pH greater than 7. So that makes sense because it's a base. And I want a pH greater than 7 for a base. All right, last one, example 4. So now I'm going the opposite direction. So just like my example 2 for my acid, I want to calculate the Kb of a solution of a 0.25 molar of a weak base, generic weak base, given its pH. So first thing I do is write out my equilibrium reaction. So some sort of weak base, B, is dissolved in water. It's weak, so we have our double arrow. The base is going to accept the hydrogen from water. Water loses its hydrogen. Now it tells us that we're looking for Kb and it's already dissociated. So that means we already have, well, we don't care about water, but we already have initial change. So we're looking at equilibrium here because it's already dissociated. The ions are already in solution. So I have a 0.25 molar base, and I'm given my pH of 9.12, but I have hydroxide ions in solution. So that means that in order to figure out this value here and this value here, which I know are 1-to-1, I have to figure out what my hydroxide ion concentration is based off of pH. So if my pH is equal to 9.12, I know that my pOH is 14 minus my pH. So 14 minus 9.12 is 4.88. And then from here, now I can get my hydroxide ion concentration, which is 10 to the negative pOH, which remember that's the opposite of our log on our calculators. So go ahead, press that, 10 to the negative pOH, so negative 4.88. And I get 1.32 times 10 to the negative 5. And that's my concentration for my hydroxide and for my conjugate acid, because it's in a 1-to-1 ratio. It just tells us it's a weak base, so we're going to assume that it's a monoprotic weak base. So I know both of those. So that means my Kb is my BH plus, OH minus over B. I know all my parts now, so I can plug those in. 1.32 times 10 to the negative 5, same for both, so that gets squared, over my concentration of my weak base. And when I plug that in, I get a Kb value equal to 6.97 times 10 to the negative 10. And that is my answer. So we'll practice more of that tomorrow, but it's basically just following the same type of equilibrium steps and rules that we've been using with since our last unit.